this computer. Great. Let me minimize our picture. Just see Greta. Okay, everything.
Okay. Hello, everyone. Good morning. I'm happy to introduce our speaker for today, Dr. Greta Toni. She recently completed her PhD, and now she's a postdoctoral researcher at University of Bologna, where she studies galaxy clusters, groups, and protoclusters. And today she will talk about the detection and multivalent characterization of these larger scale structures and what they can tell us about the galaxy evolution. So please join me to welcome our speaker, Dr. Greta.
Thank you. Thank you very much. Thank you, Ali, and thanks to the organizer for this opportunity, for inviting me. I'm Greta, and I am Italian. I'm currently based at the University of Bologna in northern Italy, but I closely collaborate with the Institute of Theoretical Astrophysics at the University of Heidelberg, which is a very nice town in Germany. I completed my bachelor in Bologna in astronomy. And then during my master, I spent some time in Germany, in Heidelberg, first studying for a semester abroad and then working on an internship for my master thesis. Then I returned to Bologna to start my PhD, keeping, of course, the collaboration with the German university. And I completed my PhD very recently, actually defended my PhD thesis in March this year. So right now I'm in the first year of my postdoctoral experience. Today, I would like to tell you a little bit about my recent research and, of course, the analysis and the results collected in my PhD thesis, which was indeed about detecting and characterizing galaxy clusters, groups, and protocluster cores with multi-wavelength data, covering approximately 12 billion years of cosmic history, or in other words, up to redshift 3.7. So galaxies in the universe are distributed across a vast and interconnected structure of filaments, walls, nodes, and voids, known as the cosmic web. The cosmic web grows hierarchically with filaments and walls funneling matter into nodes, where the most massive clusters of galaxies have the chance to form. And we can see it, for example, here in these 4 snapshots of a simulation, how a massive cluster forms as time passes from redshift 3 to the present universe. And galaxy clusters are the culmination of structure formation. Therefore, they have been long known as powerful probes of cosmology for their sensitivity to structure growth. However, the bulk of galaxies in the universe resides in these smaller associations of up to a few tens of galaxies, which are known as galaxy groups. So we can say galaxy groups occupy halo mass regime that is in between the characteristic halo masses of galaxies and those of galaxy clusters. In particular, we normally divide the galaxy groups and galaxy clusters depending on their mass. Obviously, it's not a sharp threshold, but normally we adopt as a limit 10 to the 14 solar masses, or if we want to speak about richness, so the amount of galaxies inside the system, at around 50 galaxies. So as you can imagine, as they are the most common environment for galaxies, they play a key role for the evolution of galaxies, which is shaped by the environment they grow in or they evolve in. So galaxy groups and galaxy clusters can both be detected thanks to their property, of course, and their composition. They are made of galaxies, so they are overdensities of galaxies, and they can be detected as overdensities in photometric catalogs or spectroscopic catalog of galaxies, in the optical and in the near infrared. But they also shine bright in the X-rays due to their hot ionized gas, and they also can be detected in the millimetric wavelength range. I like to show this picture that we have created for the second article during my PhD, was published last year and was selected as a picture of the month by ESA NASA web page. And as you can see here very clearly, there is a large blob, large pink blob, which is the X-ray emission of the hot ionized gas inside this system, which is in between a group and a cluster, so like a rich group and a small cluster. And of course, you can see the JWST image with this hundred of galaxies shining on the black background. And therefore, of course, you can use this kind of catalogs to detect the system as overdensities. Okay, over the past decades, wide field surveys have been used to create these large statistical samples of galaxy clusters, often specifically optimized for cosmological analysis, while structures that are smaller and fainter, like galaxy groups, but also the progenitors of a cluster at higher redshift, remain more challenging to detect and characterize. So they were often studied through targeted in-depth analysis. So the question here is, how can we actually bridge the two things? So how can we have large statistical samples of something that is hard to detect, and then that we want to characterize in depth? Well, the answer is in modern deep surveys. So modern deep surveys are nowadays allowing us to create these well-characterized samples of groups up to high redshift that we need to study growth of structure and evolution of galaxies within these structures. And in this direction, we move exactly in this direction with my recent research during my PhD. In fact, the idea was to take a detection algorithm that detects groups and clusters that is widely used on wide field surveys, applied both to data and simulations, and to use it to apply it, this algorithm is called AMICO, to apply it to a deep multi-wavelength survey that is very famous for its exceptional data richness, which is the Cosmos field. And this is a particularly innovative and challenging application that was not performed before. The Cosmos field is actually this tiny green square in the all-sky map. So before diving into the formalism behind AMICO, I would like to stress why the Cosmos field is so special and ideal for this challenging application. So the Cosmos deep field is actually not that tiny. It's a large deep field. Obviously, it invests in depth and not in wide areas we are used to for wide field surveys, but is larger than other deep fields like those observed by the Hubble Space Telescope, for instance. And it therefore samples a volume that allows us to study the large-scale structure and the formation and evolution of galaxies in the structure, which is exactly what the Cosmos field was created for. Additionally, the Cosmos field is one of the most observed patches of the extragalactic sky. So it offers access to this multi-wavelength data covering basically the entire electromagnetic spectrum from radio to X-rays, including multi-band optical and near-infrared data, which are fundamental for estimating precise photometric redshift up to high redshift, which is obviously what we need for this study. Imagine like detecting this structure in the three-dimensional space. Obviously, without a precise redshift information, we will have a lot of projection effects. Instead, the Cosmos field offers access to this high-quality photometric redshift estimates up to high redshift, which is, of course, what the AMICO algorithm is based on. So now I'm sorry, I have to go a little bit into technical details, but I promise it will be quick. So the AMICO algorithm is a pipeline for detection of cluster in photometric galaxy catalog. It is based on a formalism that is called optical linear matched filtering. And it was widely applied to wide field surveys like the Kilo Degree Survey, or KIDS for short, giving origin to cluster samples that have already been widely used for both cosmological studies, but also galaxy population analysis. And for its performances was selected as one of the two official cluster detectors in the Euclid mission. and was already applied to the very first Euclid data, the so-called quick release one. Amico doesn't need spectroscopic information for the galaxies and doesn't make explicit use of color, which in this case is quite an advantage for us because it limits the possibility of biasing the selection of clusters towards clear color features, for example, the so-called cluster red sequence. In fact, Amico detects cluster in photometric catalogs using the position of the galaxies, the photo Z, and in the simplest case, one property of the galaxies, which we normally choose to be the magnitude, in a reference band. So Amico is based on the assumption that data can be modeled as a sum of a signal component and a noise component, which account for cluster and field galaxies respectively. And the cluster component is in turn made of a model, so a template for the signal we want to detect, multiplied by the amplitude, A. The amplitude is estimated as a convolution of the data with the optimal filter, which gives an unbiased and minimum variance estimate of it. Amico creates a three-dimensional map in the space we are analyzing and attributes an amplitude value to each pixel of this three-dimensional map, and then detects candidate clusters or groups in this map at the peaks with the highest signal-to-noise ratio. Then attributes membership probability to the galaxies in the surrounding area and uses this information to actually remove the imprint of sequentially detected structures from the map in order to facilitate the detection of more blended or smaller structures. So the detection procedure goes on with this iterative detection and blending procedure until at the end the output is obviously the galaxy group or galaxy cluster catalog. So before talking about the actual output, which is obviously what we are interested in, I just wanted to mention quickly the input of a classical Amico run. Why? Because what I worked on during my PhD was a challenging and new application of this algorithm. In fact, it was the highest redshift and the deepest application of the algorithm to date. And it was run on an area, effective area, which was less than 1% of previous application of Amico to wide fields. And this made me understand how important the enhancement and the choice of input parameter is when you run such an algorithm. So the first input parameter in an Amico run is the model, the cluster model. So we need to tell the algorithm which object what we are looking for should resemble. So the expected distribution of galaxies inside the system, the cluster or the group. Allow me to use maybe the word group for simplicity, since in Cosmos we are mostly dealing with groups. Okay, so for the expected distribution of galaxies, we used the Navarro-Franken-White profile for the radial distribution and Schechter luminosity function for the magnitude distribution. And the parameters inside these functions were taken either from observed systems in the literature or from evolutionary synthesis models, so from a model. Then we have to obviously model also the distribution of galaxies in the field, which is called noise model. And normally we approximate to the overall properties of the galaxy sample we are analyzing, given that, of course, the contribution of cluster members is negligible to the contribution to the noise. And this is not trivial when the area that we analyze is very small, like in this case. So this brought me to test several techniques, and we developed a way to remove the imprint of these local overdensities from the noise model. And we also introduced regularization that smooths out the peaks in the noise model. Then we have the visibility mask, which tells the algorithm what's the accessible portion of the field that we want to analyze. And perhaps this is the most important input parameter, in my opinion, because it's also the one, its importance is always underestimated, especially when you have to deal with heterogeneous data. So, for example, when data are coming from space telescopes or ground-based facilities. which have different handling of contaminated areas. For example, you can have different image patterns. You can have foreground stars that are contaminating the field with bright star halos or different kind of spikes. Therefore, we developed a simple method that merges all this information together. So different sources of information are participating into creating the final composite visibility mask. And then we have perhaps the most trivial input parameter, which is the photometric galaxy catalog we want to base our group search on, right? Which obviously has to be cleaned in order to remove possible contaminated areas, spurious that could lead to artifact or spurious detections. Perfect. So the output finally is the catalog of candidate groups or clusters with their properties and associated galaxy member lists for each of the detections. Among the properties, we have obviously the amplitude, which I mentioned before. It's the natural output of the filtering process. And then we have the apparent richness, which tells us the amount of visible galaxies inside the system, which is just the sum of probabilities, association probabilities, and the intrinsic richness, which is the same, but with a constraint in distance from the center and magnitude. The intrinsic richness, or lambda star, was shown to be quite stable in redshift, therefore was proven also in previous studies to be a quite robust proxy of the mass of the group. Okay, so now that we have the tools to understand how we detect groups and clusters with Amico and how to apply it to a field like Cosmos, we can finally see what the first catalog that we have worked on turned out to be. The Amico Cosmos catalog. So the Amico Cosmos catalog was the first application of the Amico to the Cosmos field, in particular to the release Cosmos 2020, with a small integration from the previous release 2015, up to a redshift of 2, and down to, just for a reference, around 3 magnitude deeper than the previous application to kids. For this analysis, we performed actually 3 different independent runs. Each of these runs had a different reference photometric band. One in the R band, one was performed in the Y band, and one in the H band. So in the end, we ended up having these 3 output catalogs of groups up to redshift 2, which we then merged via 3-dimensional matching, obtaining a final catalog of more than 1,200 detections. Of these, around almost 300 detections were at redshift larger than 1.5, which is an interesting regime. We are going to explore this a little bit further later on. Obviously, like matching the different results from the 3 independent runs help us understand that most of the unmatched detections were actually having signal-to-noise ratio smaller than 3.5. Which was perhaps suggesting that 3.5 could be a good threshold to trim the catalog for a more robust sample. Given the data richness, as we said, multi-wavelength data richness of the Cosmos field, we have availability of X-ray data and X-ray based group catalogs. Therefore, we looked for X-ray counterparts to our detections. First, by comparing it to this catalog by Gassam Ghazalias in 2019. And we found 122 successful matches with this catalog. And then what we did is whenever we have an unmatched detection, we went there and measured X-ray property in the exact same data, Chandra and XMM Newton X-ray data, at the new Amico location. So for the new detections that Amico retrieved, we measure X-ray property at this location. Therefore, we end up having the matches with the initial catalog, plus the new Amico detection that have X-ray flux estimate. And this formed a sample of 622 candidates with optical and X-ray properties up to redshift 2. Once we have cleaned this group catalog, we were able to calibrate the scaling relation between the total mass coming from the X-rays and the proxies of mass that we can retrieve from Amico. You can see here an example of, on the y-axis, the total mass from the X-rays. On the x-axis, lambda star, we mentioned before, the intrinsic richness, so a proxy of mass coming directly from AMICO. We fitted the scaling relation with a redshift-dependent term, up to redshift 2 and down to less than 10 to the 13 solar masses. So we are in the group regime. Let me highlight it once more. And we found out that, for example, the Y band and the H band, so the near infrared band, seem to be more stable with respect to redshift evolution for what concerns the scaling relation between mass and mass proxies. So since we have some of our detection that are not bright in the X-rays, because not every detection had a clear X-ray counterpart, we investigated why this could be obviously odd for the richest candidates. So we investigated the impact of point source removal. So when we have extended emission in the X-ray, we want to subtract the emission from point sources, for example, AGNs. And therefore, it might be that some of the flux from extended flux is also removed. And in fact, we saw that by reintroducing this removed flux, most of the X-ray under luminous detections ended up being more consistent with the rest of the sample, except for these two cases that I highlighted here. In particular, let me focus on this one on the right that is at redshift 0.68. This one is very interesting because it was one of the richest AMICO detection, but didn't have significant X-ray emission. So we started investigating a little bit more because it was a kind of a weird object. And we found this very nice spectroscopic data from Muse that have reported already in 2021 the presence at this precise location of a double peak in redshift, in spectroscopic redshift. And therefore, we investigated, we did our spectroscopic analysis, and we found that indeed this is not a rich cluster, but is two different groups almost perfectly aligned along the line of sight and very close in redshift, perhaps along also a filamentary structure that is aligned with the line of sight. So quite an interesting one. Okay, so as this catalog was published, people started using it, and I had this wonderful opportunity to join the Cosmos Web team. And I joined the team to carry out this very, very interesting project, which was about basically taking everything we talked about so far and pushing again the limit further. So pushing it to higher redshift and pushing it to also deeper, with deeper data. And these data are from the Cosmos Web Survey. The Cosmos Web Survey is the largest continuous observation done by the JWST, the James Webb Space Telescope. And obviously, it's like a perfect marriage here, the power of James Webb and the Cosmos area and data richness. So it allows us to go even deeper, obviously on a smaller area, because it covers just a fraction of the cosmos field. So even more challenging, even more interesting. This is the result. So we were able to extend up to redshift 3.7. So we will see it. We went into the regime of progenitors of clusters, so non-virialized structures. And we have here, I put on the left the distribution in redshift. In orange, you can see the richest detections. While on the right, you have the lambda star, the intrinsic richness, versus the redshift of the detections in the catalog. For this sample in particular, we were able to perform validation against realistic mocks that we have created with the Sinfonia. Sinfonia is a Monte Carlo-based extractor of realistic mocks. So it does not rely on any simulation-like assumption. And therefore, it's data-based, encapsulates all flaws and complexity of real data. And obviously, when we validate our sample, our group sample against mocks, we are able to determine the purity and the completeness of our sample, which is the number of match detections, so successful matches, with respect to the mock over all detection and all true system for purity and completeness, respectively. And one interesting thing that we confirmed that was also found in previous studies with AMICO is that if you consider the signal to noise ratio as a characterizing property of your detections, and you bin your detections in signal to noise ratio, you find that the level of purity is more or less stable in redshift. What does that mean? This means that you can find a direct relation between a desired purity level and a signal to noise cut. So if you want, for example, a sample to be 90% pure, you know at which signal to noise you want to cut the catalog for your specific analysis. Okay, so let's talk about the elephant in the room. So what do we find at redshift larger than 2? Of course, it's not a sharp limit, once again. We have around redshift 2 this transition phase between the virialized object, the virialized clusters we observe in the present universe, and their progenitors, the so-called protoclusters. Or the other way around, if we follow the flow of time, we have a growing phase, as we can see in this sketch here, adapted from this paper, Shimakawa et al. 2018, which I really like, explains how we start from a growing phase at high redshift where there are these overdensity peaks of star-forming galaxies that then evolve. The structure has this maturing phase as time passes. There is a strong evolution of galaxies within these structures, and then this obviously collapses in the virialized system that we observe more locally. And the question here is, we are using a clustering group model. So does that actually work for detection at high redshift? Do we find something? And here I found the answer to this question in the fact that if you think of it, at high redshift, these protocluster cores that are actually the overdensity peaks inside these larger megaparsec scale regions called protoclusters, which contain a lot more also like filamentary structures. These protocluster cores, so the peaks of overdensity, have actually some kind of size and properties that can be quite similar to those of groups. In fact, by applying a cluster group model with Amico, we actually found around 500 protocluster core candidates at redshift larger than 2, between 2 and 3.7. And given that this regime was obviously like quite unexplored, to have kind of a benchmark, we compiled this list of all protocluster cores and density peaks, overdensity peaks inside the protoclusters in the Cosmos field. And we use that to match it to our detection. And what we found is that, yes, more than 200 of our detection are matched to known overdensity peaks, while 316 are the new candidate protocluster cores that were not known in the literature before this analysis. And you can see 2 examples here. The one on the left is at redshift 2.45 and 47, and the one on the right is at redshift 3.4. So obviously, as we said, these are more, given their sizes and the amount of galaxies within them, these are the overdensity peaks that are inside the larger protocluster core, the large-scale structure. Therefore, we also tried to reconstruct on a larger scale what the protocluster area could be. And we did this with quite a simple clustering analysis in 3 dimensions using the DB-scan algorithm, so very simple clustering analysis. And we found indeed that the majority of these cores that we found, these protocluster cores, are not isolated, but they are clustered in more than 100 candidate protoclusters, so what we call the candidate protoclusters. In particular, I show here the largest among them, which is a structure containing 14 different protocluster cores, which we call the Amicone or Amic1 in English, because it was the first and the largest protocluster candidate found in real data by Amico. Okay, so now that we have talked about the detection of these systems, And we have described these two different catalogs, two different resources. We can move to the second part of my PhD thesis, which was about characterizing these systems that we have detected. And the first and most natural application, perhaps, of this kind of catalogs is the study of the galaxy population within them, in particular of the build-up of the quiescent population characteristic of these systems. And as I started working on this project, I immediately faced perhaps one of the biggest classification problems of extragalactic astrophysics, which is classifying galaxies into quiescent and star-forming. So normally in the literature, there are several methods that are often sharp cuts, like empirical cuts in color diagram, color redshift. So my question was, is there a way to put these sources of information together and actually take the advantage from each of them and perhaps learn something more, especially about those galaxies lying close to the boundaries? And the answer is machine learning. Machine learning can do that. So I try to experiment a bit with some algorithms, starting from feature engineering on my data. So I studied the impact of different features, which I chose to be the rest frame magnitudes. Then obviously we should address also class imbalance, because this is a highly imbalanced problem, since in real data you normally have much more examples of star-forming galaxies rather than quiescent. And then we can consider also the sparsity awareness, so the ability of an algorithm, of a model, to include the information from missing data. So I trained several combination of algorithms and methods and tested them. I tested their performance with standard metrics, so precision recall, F1 score, basically the equivalent of purity and completeness. But I also consider the reliability of the probability, which is exactly what we are interested in, the probability for of a galaxy being quiescent, for example. And the winner was XGBoost, which is a very popular algorithm, like a gradient boosting decision tree, which we trained on rest frame magnitudes, available rest frame magnitudes, achieving over 95% of purity and 91% of completeness. So this model was then applied to our galaxy sample, and therefore each galaxy in our sample have a probability of being quiescent, and the complementary, of course, of being star-forming. So we use this information to then compute the quiescent galaxy fraction, the fraction of quiescent galaxies inside each group, using the probability of being a member of the system conditional to the probability of being red or blue or quiescent star-forming. And we found that the quiescent galaxy population seems to build up steadily, starting from around redshift 2. And this growth seems to be also slightly earlier and accelerated for the richest groups, which is interestingly consistent with the other studies on more massive and more local clusters. We tested also a different approach. Since the the membership probability from Amico contains a sort of model dependence, we developed these new cylinder methods, which allows instead for a nearly model independent approach. It works simply by taking cylinders around each detections and performing a background subtraction. And this ended up confirming the trends that we have seen with the previous method. Additionally, since we have X-ray, we have mentioned it before, we wonder if there was a correlation between the quiescent galaxy fraction and the emission in the X-rays. And we found that X-ray faint groups have on average lower quiescent fraction than those that are bright in the X-rays. And they are also found to be more numerous in filaments with respect to the nodes and the area around the nodes. Another way we have to characterize the quiescent population in a system, in a galaxy system, like a group or a cluster, is to actually study the red sequence. The red sequence is the grouping of red quiescent galaxies in the color magnitude space. And to do so, to identify red sequences in our sample, we fitted a relation in the color magnitude diagram for each group and studied the property of the best fitting relation, the red sequence line. So we identified 225 red sequence ridgelines using both the rest frame magnitude and the rest frame matched observed magnitude. We studied the slope, the scatter, the average intercept, all the parameters of the best fitting line, and we found no significant evolution of the slope and the scatter with redshift, which is consistent with previous results. So we can say basically that this analysis ended up being a sort of extension of previous studies in the literature into the group regime and into a more distant universe. Speaking of distant universe, actually the highest redshift red sequence that we have identified is represented by the star in the plots here on the right, and is located at redshift 3.4. If confirmed spectroscopically, this might be one of the highest redshift, one of the earliest red sequence detected today. And I wanted to show it to you here quickly. Like on the left, you have the overdensity, the protocluster cores, with a zoom on the 3 quiescent galaxies. It's quite compact, actually. These 3 quiescent galaxies are grouping in the color magnitude diagram, which is on the right. As you can see, they have very similar colors and also consistent with the model at this redshift. So the expected color for a quiescent galaxy. Perfect. So the last topic I would like to talk about is brightest group galaxies. So in general, central galaxies in clusters are very important because they are thought to be the aftermath of a complex evolutionary path, and therefore are often used as laboratory to study the impact of the environment on galaxy evolution. And there are many studies in observation and simulation that have shown that cluster centrals, especially in massive clusters and lower redshift, are massive elliptical galaxies that are evolving passively. They're equivalent in groups, so brightest group galaxies or BGGs are instead a little bit less studied and less understood. And they have shown there is evidence in recent studies that some of these galaxies might be characterized by higher star-forming activity and perhaps like different evolutionary pathways with respect to their cluster equivalent. So what we have done is, since we had our group catalog, we performed BGG selection to create our BGG catalog. To select the BGGs, we use obviously vicinity to the group center, magnitude, and as a last optional selection criteria, the membership probability. Then we have selected, we have looked for star-forming ones, in particular with star formation rate larger than 20 solar masses per year, and we found some. And we thought of trying to explore the properties of molecular gas, because one would expect that if a galaxy is star-forming, in this case, is hosting a reservoir of molecular gas fueling this star formation. And so we restricted ourselves to a redshift range that would make observation feasible at the IRAM 30-meter telescope, which is a radio telescope 30-meter diameter in Granada, Spain. We submitted a proposal and got some observation time for these 3 galaxies here. So these 3 BGGs, as you can see, they are located at around redshift 0.3, and they have very particular morphologies, very disturbed. They show signs of interaction, close companions, tidal features, also substructures of different colors. Therefore, we were wondering what were the properties of the molecular gas, and this we can tell thanks to CO observations, which we carried out at the IRM telescope. Here is a photo of me doing the observations there. It was such a great experience. So, given the star-forming nature, also the morphology, the complex morphology, and indeed the star-forming nature that was confirmed not only by the colors but also by several star formation rate indicators, one would expect these galaxies to host a large molecular gas reservoir. Instead, only one, the second one, was found to have a clear detection in emission for the CO. The CO is, of course, a carbon monoxide, and it is an excellent tracer of molecular hydrogen, so called gas that could be fueling star formation. Okay, so only the second one had the clear detection, and for the other two, we were able to establish upper limits. Therefore, what is this telling us? That these galaxies, perhaps even if they have kind of similar properties, like similar mass, similar star formation rates, they could be actually caught in different phases of their evolution. For example, the first one seems to be like having an ongoing or recent interaction that perhaps triggered star formation. Perhaps there was an enhanced event of star formation, but the gas is not observed, maybe because there is no replenishment of gas due to environmental processing. So consumption of gas without replenishment. The second one has a large reservoir of molecular gas. We can see also different substructures in different colors. So it has a red central structure with blue clumps around it, probably exactly where the star formation is occurring. And then we have the third one, which is kind of similar to the first, but the main difference is that it has a depletion time, so time scale in which the gas is depleted, that is much smaller than the first one, and much smaller, like around a third of typical main sequence galaxy values. So this is perhaps telling us this is a rapidly evolving galaxies which will rapidly be quenched. Great. So what we did was also we compared our results to the literature, and in particular, we found that in terms of star formation rate and molecular properties, our three galaxies, obviously it's just a pilot sample, so we can't tell much, but it seems like this could be these galaxies could be occupying a region that is in between extremely star-forming cold gas-fed BCGs in cool clusters, and more quenched brightest central galaxies in clusters like those in the kids sample that you can see here in orange. Perfect. So this leads me to the conclusions. We'll have a quick sip of water. Okay, so as I go through the conclusion, summarizing what we have talked about today, I will also quickly highlight some future research directions. So I like to divide in four main areas my recent research work. So first of all, during my PhD, we have created these publicly available catalogs with multi-wavelength properties that can be accessed, that can be used. In fact, they are being used by several independent groups, which is great. They're doing amazing science. It's very nice to see for me. We have the Amico Cosmos catalog, which extends up to Redshift 2 on the full Cosmos area. with optical and X-ray properties. And then we have the most recent brother of this catalog, the Cosmos Web Group and Protocluster Core catalog, which instead is focused on the Cosmos Web portion of the Cosmos field, goes much deeper and to higher redshift, 3.7, so it's ideal for studying growth of structures and protoclusters. And among the possible ideas for the future, well, I'm currently working because I'm quite interested in the difference between X-ray faint, X-ray bright, so the comparison between optical and X-ray properties. And I'm also working on the on completing the group mass estimation in these catalogs. And then we contributed, of course, a bit to the advance of methodologies for the detection of structures. With the routine for the noise cleaning and regularization, the one for creating composite visibility mask to adapt and enhance the algorithm to this challenging application. And of course, we applied for the first time the Amico algorithm to protocluster detections in real data, which will be very useful in Euclid. Actually, already the application to the first data was leveraging a bit of the data cleaning and exercises that we did in this work for the Amico model and the masking. For what concerns evolution of galaxies, we studied the buildup of quiescent population over across 12 gigayears, almost 12 gigayears of cosmic history. And we then had this pilot project at the IRM telescope to target molecular gas in star-forming central galaxies in group, which we hope to keep exploring with our millimetric campaign, and also connecting this with the properties of the hosting group, of the hosting halo. And finally, for what concerns distant universe and rare system, we detected more than 300 new candidate protocluster cores at redshift larger than 2. And including this compact overdensity of quiescent galaxies at redshift 3.4. Obviously, this leaves space for spectroscopic confirmation of redshift, of quiescence as well, and in general of for multi-wavelength follow-ups. So I leave you here with this image that shows all the systems we have detected during these years, and some of the, in my opinion, most interesting and weird detections. I thank you very much for listening, for your attention, for this amazing opportunity. And yeah, I'm happy to take questions, and let's chat if you want to use the catalog, if you have ideas. If you have longer questions, this is my email. And if you use LinkedIn, let's connect. Thank you very much.
Thank you so much, Greta. That was a great talk. We have time for questions. Oh, Ali has a question. Oh, we have also online participant. They can also ask questions if they have.
Great.
I don't see anything online. Ali?
Hi, thank you for the great talk. So I have a quick question about the Amico algorithm.
Yeah.
You said you don't use the spectroscopic redshift and also color. And I want, you use galaxy positions and magnitude and photometric redshift to detect clusters, right?
Yeah, exactly. So the redshift information is encapsulated in the photo Z, so in the photometric redshift.
Yeah.
So obviously not a single value like a spec Z, but a probability distribution. Normally we use we approximate it to a Gaussian with the errors taken from the photometric catalog, and this is how we incorporate the redshift information. But for the rest, it's just position in the sky, redshift, and in the cases in which that I presented, and also as we normally do with Amico, also in Euclid, the use of a magnitude in a single reference band.
Yeah, thank So I think you
And
explained.
the way it does it is like as a looking for resemblance to a model that we give to the algorithm, where the distribution in space and magnitude is defined.
Right. Yeah. And I think you talked about it in one of your slides, but since the photometric redshifts are like have large uncertainty, could that cause a problem, for example, like especially at higher redshifts?
Yeah, absolutely. Yeah, of course, we are dealing with photometric redshift, so they have their uncertainty, and it's important to include them in the information. That's why we use the redshift probability distribution. And the way we use that in Amico is actually that we weight the contribution. So inside the membership probability computation, we use the information of the redshift and we weight the contribution of the galaxy for the value of the redshift probability at the redshift of the cluster candidate or group candidate. And of course, as you said, there is an impact if we have bad redshifts or bad distributions of redshift, like very large errors.
Yeah.
But generally, that's why we have to deal with very good data, like those provided by the Cosmo Web Survey. That was the perfect occasion to test this algorithm because the photometric redshift, they are photometric, but they are great and they have very small error. They are very precise. And interestingly, it's not only a problem of how large the errors are. Sometimes the problem is even that the error are too small. In fact, since we weight the contribution of each galaxies for the value of the photo-Z distribution at that redshift, sometimes if the distribution is very narrow and slightly off, then the probability of belonging to that structure is smaller. So this is something very interesting that we found, and we was also useful for the Euclid analysis.
Thank you so much.
Thank you.
Do you have any other questions online? Person? Okay, perfect. So let me ask a quick question. Can you please go back to the brightest group galaxies? I have a quick question on the selection criteria that you mentioned.
Of course.
Okay.
Oh, too much. Okay.
Yeah, so you talk about choosing these galaxies in these groups in this redshift range with SPECs. Why do you put this SFR limit for your selection?
Okay, so yeah. So the SFR limit was kind of not arbitrary, but we obviously wanted to restrict ourselves to the most star-forming structures. So those for which we could see the star formation rate was higher than this threshold, which is normally what is used in the literature. So we kind of followed a previous campaign that studied the brightest cluster galaxies inside, for example, kids. So like the equivalent in clusters, because our goal was also to compare them. And for what concerns instead the redshift interval, we tried to go as distant as possible because in this redshift range, the literature lacks a bit statistical samples of these kind of galaxies. So we tried to go as high as possible, but obviously without compromising too much the feasibility of the observation with this antenna, 30-meter antenna. Yeah, I hope that answers your question.
Yeah. And how many in total do you find?
Just these three.
Okay, yeah, I was like, okay, I wanted to make sure that you only find 3 of them.
Yeah, exactly.
And
Exactly. So far, yes. Actually, this one, sorry, I would like just to add something quick, that these 3 galaxies were extracted from the Amico Cosmos sample, so the first one that I presented. However, since these galaxies have to have spectroscopic redshift at that time when we extracted, spectroscopic coverage was more restricted with respect to now. Spectroscopic coverage is growing and it's very large in the Cosmos field. Plus, now we have the groups of the Cosmos Web. So this pilot study was just the beginning of the campaign, and we are thinking of expanding this with the current spectroscopic coverage and with the deeper observations that we have for Cosmos Web. So for sure, I mean, hopefully we will also find other examples.
Cool, very cool. Thank you so much. Let's thank Greta one more time.
Thank you very much. Thank you all.
Thank you.
Have a nice day.
You as well. We will put this recorded video on YouTube and we can share the link with you for sure.
Amazing. Thank you very much.